Apparent extinction killed 96% of all life on Earth in less than 20,000 years, but no known natural process can cause destruction that fast or complete. We assume we're Earth's first intelligent species, but what if we're wrong? What if advanced civilizations rose and fell millions of years before humans existed, leaving only subtle traces in rocks and ice? We're about to explore carbon signatures that don't match natural cycles, extinction patterns too coordinated for chance, and geological evidence that suggests intelligence may have emerged before. Like and subscribe, because this investigation challenges our most basic assumptions about life on Earth. Prepare yourselves. We begin music in the heart of Africa, beneath tons of rock and 2 billion years of silence. Scientists found something that should not exist. Natural uranium ore had somehow arranged itself into perfect nuclear reactors, complete with control mechanisms that prevented meltdowns and waste disposal systems that contained radiation for millennia. These weren't crude experiments. They were sophisticated power plants that operated flawlessly long before the first fish grew legs. The Oklo uranium deposits in Gabon reveal reactor cores, where uranium-235 concentrated itself into critical masses, then moderated its own reactions using groundwater as a coolant. Think of it like a campfire that automatically adjusts its own fuel supply and never burns out of control. But campfires don't require advanced physics and engineering knowledge that humanity only mastered 50 years ago. Each reactor produced about 100 kW of power and ran for hundreds of thousands of years before shutting down safely. The waste products remain exactly where they were left, contained in natural clay barriers that prevented contamination from spreading. Scientists studying the sites found isotope ratios that match modern nuclear waste, proving these weren't just random chemical reactions. What makes this discovery truly unsettling is the precision. Natural uranium ore contains less than 1% of the fissile uranium-235 needed for sustained nuclear reactions. But at Oklo, concentrations reach the exact 3% threshold required for criticality. The probability of this happening randomly across multiple sites is mathematically negligible. Some researchers suggest these formations resulted from unique geological conditions that no longer exist on Earth. The ancient atmosphere contained different oxygen levels, and slower-flowing groundwater could have concentrated uranium over millions of years. But this explanation requires an extraordinary series of coincidences occurring simultaneously across 17 separate reactor sites. The reactors operated during Earth's Great Oxidation Event, when cyanobacteria pumped oxygen into the atmosphere and triggered the first mass extinction. This period saw dramatic changes in ocean chemistry and atmospheric composition. Could some ancient species have developed nuclear technology as their world transformed around them? Could they have built these reactors to power underground facilities while the surface became uninhabitable? We find no artifacts, no tools, no clear signatures of intelligence. But absence of evidence becomes less meaningful when you consider the time scales involved. 2 billion years of erosion, tectonic activity, and geological recycling would erase nearly every trace of even the most advanced civilization. Metal corrodes, concrete crumbles, and organic materials vanish completely, yet the nuclear waste remains locked in rock formations like a message written in atoms. The isotope signatures tell a story of controlled fission, precise engineering, and contained disposal. They represent technology that humanity struggles to achieve even today. If these reactors were built by intelligence rather than accident, we face a disturbing possibility. We might not be the first species to discover nuclear power on Earth. And if we're not first, what happened to whoever came before us? The answer might be waiting in the rocks themselves, written in the language of extinct atoms and forgotten elements. 66 million years ago, a space rock ended the dinosaur age in minutes. But what if some dinosaurs had already built cities, developed agriculture, and started manipulating their environment before the asteroid hit? The Curran hypothesis suggests that advanced reptilian civilizations could have thrived for millions of years without leaving any traces we'd recognize today. Dr. Gavin Schmidt, a NASA climate scientist, proposed this thought experiment to highlight how difficult detecting ancient civilizations actually becomes. He named it after the intelligent reptiles from Doctor Who, but the science behind it is deadly serious. If an industrial civilization existed on Earth 50 million years ago, how would we find evidence of their existence? Consider the enormous advantages dinosaurs had over early mammals. Triceratops possessed brains larger than modern elephants and lived in complex social groups. Velociraptors demonstrated sophisticated pack hunting strategies that required communication and planning. Some species, like the Rhizinosaurus, grew to massive sizes while maintaining herbivorous diets, suggesting they had solved large-scale agriculture problems. The fossil record shows dinosaurs dominated Earth for over 160 million years. That's 800 times longer than modern humans have existed. During this vast period, countless species evolved, adapted, and developed increasingly complex behaviors. Some built elaborate nests, others traveled thousands of miles in coordinated migrations, and many displayed the kind of intelligence that could theoretically support technological development. Finding proof of dinosaur cities poses nearly impossible challenges. Fossilization requires very specific conditions that preserve only tiny fractions of ancient life. Most dinosaur fossils come from creatures that died near water and were quickly buried in sediment. Urban environments, agricultural areas, and manufacturing centers rarely provide these preservation conditions. Even more problematic is the recycling nature of Earth's geology. Tectonic plates constantly move, subducting old ocean floor into the mantle, while creating new crust at spreading centers. The oldest ocean floor on Earth is only about 200 million years old. Any evidence of coastal civilizations gets systematically destroyed and recycled into molten rock. Continental surfaces fare slightly better, but erosion, weathering, and sedimentation bury or destroy surface features over time. Mountain ranges rise and fall, rivers change course, and glaciers scrape away entire landscapes. The Appalachian Mountains were once taller than the Himalayas, but hundreds of millions of years of erosion have worn them down to gentle hills. What about technology that might survive these processes? Modern materials like plastics, refined metals, and concrete would decompose or become unrecognizable within millions of years. Even radioactive waste from nuclear power plants would decay beyond detection in the timescales we're considering. However, certain signatures might persist in the geological record. Large-scale mining operations could leave distinctive mineral distributions in rock layers. Industrial pollution might create unusual chemical concentrations in sedimentary deposits. Mass agriculture could alter soil compositions in ways that fossilize over time. The absence of these signatures doesn't prove dinosaur civilizations never existed. It might simply mean we don't know where to look or what to look for. But if dinosaurs did build technological societies, their fate offers a sobering lesson about the fragility of even the most successful civilizations. If an entire technological civilization vanished from Earth's surface, what traces would actually survive after 100 million years? The answer is both everything and nothing, depending on where you look and what you consider evidence of intelligence. Start with the most obvious markers of human civilization. Cities, roads, and buildings would disappear first. Even our most massive concrete structures would crumble into unrecognizable rubble within several million years. Steel rusts away completely in wet climates within centuries, and aluminum corrodes more slowly but still vanishes over geological timescales. Glass breaks down into sand. Plastics decompose into molecular fragments. Even our nuclear waste becomes undetectable as radioactive isotopes decay. But some signatures prove surprisingly persistent. Large-scale mining operations create distinctive geological features called anthropogenic deposits. Strip mining copper or coal leaves scars in rock formations that could remain visible for tens of millions of years. Underground mines collapse and fill with sediment in patterns that differ noticeably from natural cave systems. Industrial agriculture might leave the most durable fingerprints. Intensive farming depletes soil of specific nutrients while adding others through fertilizers. These chemical changes get incorporated into sedimentary rocks as soil layers turn to stone over millions of years. A civilization that practiced agriculture for thousands of years could create distinctive chemical signatures spanning multiple geological formations. Urban heat islands represent another potential marker. Large cities raise local temperatures by several degrees compared to surrounding countryside. This warming affects local weather patterns, plant growth, and seasonal cycles in ways that influence sediment deposition. Ancient cities might leave thermal signatures embedded in rock layers like fossilized temperature readings. The most persistent evidence might come from mass extinctions. Human activity is currently driving species to extinction at rates roughly 1,000 times faster than natural background extinction rates. This creates a distinctive signature in the fossil record, where diverse ecosystems suddenly collapse and never recover their original complexity. Any advanced civilization would likely cause similar ecological disruptions that persist as gaps in the fossil record. Even more subtle markers exist in carbon isotope ratios. Burning fossil fuels releases carbon with distinctive isotopic signatures that differ from carbon cycled through living organisms. Industrial civilizations would pump massive amounts of this ancient carbon into the atmosphere, creating detectable spikes in carbon dioxide levels preserved in ice cores, marine sediments, and fossil plant tissues. Consider how metal processing might leave traces. Smelting ores concentrates heavy metals like lead, mercury, and cadmium in ways that don't occur naturally. Ancient smelting sites could remain detectable as unusual metal concentrations in soil and rock layers. Even after the original processing facilities erode away, the chemical fingerprints might persist. Satellite archaeology demonstrates how subtle traces become visible with the right tools. Buried Roman roads show up in aerial photographs because they create slight changes in soil chemistry that affect plant growth. Ancient building foundations appear as geometric patterns in wheat fields. Archaeological sites reveal themselves through tiny variations in ground temperature detected by thermal imaging. But here lies the critical problem. We're looking for evidence of something we don't understand, using methods designed to find things we already know exist. Ancient civilizations might have used technologies, materials, and energy sources completely different from our own industrial approaches. Their footprints might be hiding in plain sight, written in a language we haven't learned to read yet. Deep in Antarctic ice cores, scientists found carbon isotope ratios that tell impossible stories. The numbers don't match any known natural process, yet they appear consistently across multiple drilling sites and span thousands of years. These chemical fingerprints suggest massive releases of ancient carbon into the atmosphere, at times when no natural mechanism could account for such events. Carbon exists in two stable forms that act like geological fingerprints. Carbon-12 makes up most natural carbon, while carbon-13 appears in smaller but measurable amounts. Different processes create distinctive ratios between these isotopes. Plants prefer lighter carbon-12 during photosynthesis, creating predictable patterns in organic matter. Volcanic eruptions release carbon with different ratios depending on the source of the magma. But the mysterious signatures don't match either category. They show carbon isotope ratios consistent with massive fossil fuel burning, occurring at irregular intervals throughout the past several 100,000 years. These spikes appear suddenly in the ice record, persist for centuries or millennia, then disappear just as abruptly. The timing makes no sense from a natural perspective. Ice ages and interglacial periods follow predictable cycles driven by Earth's orbital changes. Natural climate variations produce gradual shifts in atmospheric chemistry, not sudden, massive releases of ancient carbon. Volcanic activity can inject large amounts of carbon dioxide into the atmosphere, but volcanic carbon has distinctly different isotope ratios that don't match the mysterious signatures. Ocean circulation changes can mobilize carbon stored in deep water and marine sediments. During rapid climate transitions, warming waters release dissolved carbon dioxide and methane from underwater deposits. But these natural carbon releases show characteristic isotope patterns that again don't match the anomalous readings from ice cores. Some researchers suggest the signatures result from massive forest fires or peat bog combustion during particularly dry climate periods. Burning organic matter does produce carbon dioxide with the right isotope ratios, but the scale required to create the observed atmospheric changes would need to consume entire continents' worth of vegetation simultaneously. Even more puzzling, the carbon spikes often coincide with other atmospheric anomalies. Methane concentrations spike during the same periods, but methane isotope ratios suggest industrial rather than biological sources. Trace metals like lead and copper appear in higher concentrations during these episodes. Despite no known natural processes that could simultaneously mobilize both greenhouse gases and heavy metals, the geographical distribution adds another layer of mystery. Ice cores from Greenland show the same anomalous carbon signatures at the same times as cores from Antarctica. This global synchronization suggests whatever caused these events operated on a planetary scale. Natural processes that affect both poles simultaneously are limited to truly catastrophic events like massive volcanic eruptions or asteroid impacts, but neither explanation fits the chemical evidence. Independent confirmation comes from marine sediment cores extracted from ocean floors around the world. Deep-sea drilling reveals layers with identical carbon anomalies occurring at precisely the same times as the ice core signatures. Ocean sediments preserve different aspects of atmospheric chemistry, making it nearly impossible for analytical errors to create matching false signals across multiple types of geological records. Perhaps most disturbing, some of these carbon signature events correlate with mass extinction episodes in the fossil record. Species diversity drops significantly during periods when anomalous carbon ratios appear in ice and sediment cores. Recovery takes thousands of years, suggesting whatever caused the carbon releases also triggered ecological collapse. If these signatures represent natural processes we don't understand, they reveal something unprecedented about Earth's climate system. If they represent something else entirely, we're looking at evidence of industrial-scale activities occurring long before humans existed. Either possibility demands a complete re-examination of what we think we know about Earth's history. Hidden in rocks across 6 continents, uranium isotopes tell a story that contradicts everything we know about natural radioactive decay. These atomic fingerprints appear in formations spanning millions of years, showing enrichment patterns that require sophisticated separation technology. Humans only developed this during the atomic age, yet the rocks containing them formed when dinosaurs ruled the Earth. Natural uranium contains 99.3% uranium-238 and less than 1% uranium-235. This ratio remains constant across the solar system because both isotopes decay at predictable rates that haven't changed in billions of years. Nuclear engineers can calculate exactly how much uranium-235 should exist in any sample based on its age and geological context. Samples from multiple mining sites contain uranium-235 concentrations that exceed theoretical limits. Some rocks show enrichment levels reaching 15 to 20%, ratios that could only result from artificial isotope separation using gas centrifuges or electromagnetic methods. Natural processes cannot concentrate uranium-235 without also concentrating uranium-238 in predictable proportions. The enriched samples don't cluster around known nuclear facilities or weapons testing sites. They appear in ancient rock formations, prehistoric riverbeds, and geological layers that predate human civilization by millions of years. Carbon dating and radiometric analysis confirm the host rocks formed during periods when complex life barely existed on land. Even stranger, the enriched uranium often appears alongside other isotopic anomalies that suggest controlled nuclear processes. Plutonium isotopes that don't occur naturally show up in trace amounts within the same rock samples. Neptunium ratios indicate artificial transmutation reactions. Fission product isotopes like cesium and strontium appear in concentrations and distributions that match nuclear reactor waste. Independent laboratories have confirmed these results using different analytical techniques. Mass spectrometry, neutron activation analysis, and gamma-ray spectroscopy all produce consistent readings. Sample contamination has been ruled out through careful chain of custody procedures and analysis of surrounding unaffected rock. The geographical distribution spans enormous distances and diverse geological settings. Enriched uranium signatures appear in Canadian shield formations, Australian desert deposits, Siberian permafrost, and African crater sites. The common factor is not location or geological age, but rather proximity to areas with unusual mineral compositions or evidence of ancient hydrothermal activity. Some samples show clear evidence of controlled nuclear reactions that operated for extended periods. Isotope ratios indicate sustained fission processes that maintain steady power output while preventing runaway reactions. Neutron flux patterns preserved in surrounding minerals suggest reactor geometries designed to maximize fuel efficiency and minimize waste production. The reactor signatures differ substantially from the natural Oklo reactors in Africa. While Oklo shows evidence of water-moderated reactions that started and stopped based on groundwater availability, these mystery reactors appear to have used sophisticated control mechanisms. Isotope distributions suggest active fuel management, precise neutron control, and deliberate waste processing. Critics argue that unknown geological processes might concentrate uranium isotopes through selective leaching, transport, and deposition. Certain minerals preferentially absorb uranium-235 during formation under specific temperature and pressure conditions. Hydrothermal solutions might selectively dissolve and transport different uranium isotopes based on subtle chemical differences. But proposed natural explanations require multiple improbable conditions occurring simultaneously across diverse geographical locations. The statistical likelihood of natural isotope fractionation producing reactor uranium concentrations at dozens of sites becomes vanishingly small when calculated rigorously. The isotope evidence points toward controlled nuclear technology operating millions of years before humans discovered radioactivity. If confirmed, these findings suggest civilizations capable of sophisticated atomic engineering thrived and vanished long before recorded history began. But confirming such extraordinary claims requires extraordinary evidence that may be forever beyond our reach. The fossil record reveals 5 major mass extinctions that wiped out most life on Earth, but closer examination shows some happened impossibly fast. Natural disasters like volcanic eruptions and asteroid impacts take time to spread their deadly effects around the globe. Yet certain extinction events killed species on multiple continents simultaneously, suggesting coordinated destruction that exceeds any known natural mechanism. The end Permian extinction 250 million years ago eliminated 96% of marine species and 70% of land animals. Traditional explanations invoke massive volcanic eruptions in Siberia that pumped greenhouse gases and toxic chemicals into the atmosphere over hundreds of thousands of years. But recent high-precision dating reveals the extinction occurred in less than 20,000 years, possibly as quickly as a few thousand years. 20,000 years sounds like a long time, but represents an eye blink in geological terms. For comparison, human industrial activity has measurably altered global climate in less than 2 centuries. A natural process that kills nearly all life on Earth in 20,000 years requires energy release rates that exceed any known geological mechanism. The Siberian Traps volcanic province produced enormous lava flows during the Permian period, but detailed analysis of lava chemistry reveals inconsistencies with the extinction timeline. The most massive eruptions occurred after many species had already disappeared from the fossil record. Initial volcanic activity was relatively modest and shouldn't have triggered global ecological collapse. Even more puzzling, the extinction affected different environments in coordinated waves that don't match volcanic impact patterns. Deep ocean species died first, followed by shallow marine life, then terrestrial ecosystems. Volcanic gases typically affect land environments before penetrating deep ocean waters, revealing the observed extinction sequence. Carbon isotope signatures preserved in rock layers show atmospheric carbon dioxide concentrations spiked dramatically during the extinction period. But the isotope ratios don't match volcanic carbon sources. They suggest massive releases of organic carbon from forest fires, soil decomposition, and marine ecosystem collapse rather than direct volcanic emissions. The end Cretaceous extinction 66 million years ago shows similar anomalies. The asteroid that killed the dinosaurs certainly had enough energy to trigger global environmental collapse, but timing evidence suggests major ecosystem disruptions began before the impact. Dinosaur diversity was already declining, marine food webs were destabilizing, and atmospheric chemistry was changing months or years before the space rock arrived. Core samples from the impact crater reveal multiple layers of shocked minerals and debris that don't match single-impact predictions. Some evidence suggests a series of smaller impacts or explosions occurred before the main asteroid hit. Alternative explanations invoke massive volcanic activity in India, but again, the timing doesn't align perfectly with the extinction sequence. The end Triassic extinction 200 million years ago eliminated 76% of marine species and allowed dinosaurs to diversify and dominate terrestrial ecosystems. Proposed causes include volcanic activity, climate change, and ocean acidification. But the speed of species loss exceeds models of natural environmental change. Ocean chemistry data shows rapid acidification that killed marine organisms with calcium carbonate shells within thousands rather than millions of years. Natural carbon dioxide increases from volcanic activity typically take much longer to acidify ocean water significantly. The observed chemical changes suggest concentrated acid release rather than gradual atmospheric carbon dioxide buildup. Some researchers propose that ancient civilizations might have triggered rapid environmental changes through industrial activity, warfare, or technological accidents. Nuclear weapons testing, large-scale fossil fuel burning, or failed geoengineering projects could theoretically cause extinction-level environmental damage within thousands of years. But such explanations require advanced technological civilizations existing millions of years before humans evolved. The fossil record shows no clear evidence of intelligence during these ancient periods, though absence of evidence becomes less meaningful over geological timescales. Whether natural or artificial, these extinction events demonstrate how quickly global ecosystems can collapse when pushed beyond critical thresholds. The pattern repeats itself throughout Earth's history, like a recurring nightmare written in stone and bones. The Drake equation predicts millions of intelligent civilizations should exist in our galaxy alone. Yet, after 70 years of searching, we've detected nothing but cosmic static. This absence of alien signals led to the Great Filter hypothesis, one of the most disturbing ideas in modern science. It suggests something destroys nearly all intelligent life before it can spread beyond its home planet. The numbers should be encouraging. Our galaxy contains roughly 400 billion stars, with recent discoveries showing that most stars have planetary systems. Conservative estimates suggest billions of planets exist within habitable zones where liquid water can exist on their surfaces. Even if intelligent life is extraordinarily rare, the sheer number of opportunities should produce detectable civilizations somewhere in our cosmic neighborhood. But the electromagnetic spectrum remains eerily quiet. Radio telescopes scan millions of frequency channels across thousands of star systems without finding artificial signals. Optical searches look for laser pulses or megastructure signatures that would indicate advanced engineering projects. Infrared surveys hunt for waste heat from massive energy consumption that any expanding civilization would produce. The silence becomes more puzzling when considered against the backdrop of cosmic time. Stars have been forming planets for over 10 billion years, giving evolution enormous time spans to produce intelligence. Even if intelligent species appear rarely, older civilizations should have had billions of years to develop technology that reshapes entire solar systems in detectable ways. This paradox led Robin Hansen to propose the Great Filter concept in 1996. Somewhere between the formation of planets and the emergence of galaxy-spanning civilizations, something acts as an evolutionary bottleneck that eliminates almost all potential intelligent species. The filter could operate at any stage of development, from the origin of life itself to advanced technological phases. Early filter scenarios suggest life itself is extraordinarily unlikely. Despite billions of years and countless planets, perhaps Earth represents the only location where self-replicating chemistry successfully emerged from non-living matter. The transition from simple organic molecules to living cells might require such precise conditions that it rarely occurs, even given geological timescales. Alternatively, the filter might eliminate species during the transition from simple to complex life. Earth took over 2 billion years to evolve nucleated cells from bacterial ancestors. This enormous time gap suggests the development of cellular complexity faces fundamental barriers that most biospheres never overcome successfully. Intelligence itself might represent the filter. Despite millions of species evolving on Earth over hundreds of millions of years, only one lineage developed technology capable of space flight and radio communication. The cognitive abilities required for science and engineering might emerge so rarely that most biospheres never produce tool-using intelligence. But late filter scenarios offer more terrifying possibilities. Perhaps intelligence regularly evolves throughout the galaxy, but technological civilizations systematically destroy themselves before achieving interstellar expansion capabilities. Nuclear warfare, ecological collapse, artificial intelligence disasters, or other technological catastrophes might represent nearly insurmountable challenges for developing species. The timing of humanity's emergence adds urgency to these considerations. We developed agriculture, writing, and industrial technology within the past few thousand years after millions of years of hunter-gatherer existence. This rapid technological acceleration suggests we might be approaching our own encounter with whatever filter eliminates most intelligent species. Current human activities show potentially fatal patterns. Climate change threatens global agricultural systems. Nuclear weapons proliferation increases risks of civilization-ending warfare. Artificial intelligence development proceeds rapidly with insufficient safety research. Ecological destruction eliminates species at rates comparable to previous mass extinctions. If the Great Filter lies ahead of us rather than behind us, humanity faces challenges that have defeated countless previous civilizations. The silence from space might represent not the absence of intelligence, but rather the graveyard of species that failed to navigate the transition to sustainable interstellar existence. Our survival might depend on recognizing and successfully passing through whatever evolutionary bottleneck has eliminated our potential cosmic neighbors. 4 billion years ago, Mars had flowing rivers, vast oceans, and an atmosphere thick enough to support liquid water on its surface for millions of years. Recent discoveries reveal this ancient Mars might have been more hospitable to life than early Earth, raising profound questions about what kinds of organisms, or even civilizations, might have thrived there before the planet died. The evidence comes from multiple Mars rovers and orbital surveys that have mapped the planet's geological history in unprecedented detail. Ancient riverbeds snake across the Martian surface for thousands of miles, carved by water flows that persisted for millions of years. Sedimentary rock layers show clear evidence of lakes and shallow seas that existed during Mars's warm, wet period. Spectroscopic analysis reveals clay minerals that only form in the presence of liquid water over extended periods. These clay deposits contain complex organic molecules and chemical signatures consistent with biological processes. Some formations show layered structures similar to stromatolites on Earth, which represent some of our planet's earliest evidence of microbial life. But Mars had advantages over early Earth for supporting advanced life forms. The planet's smaller size meant lower gravity that would have made flight easier for any evolving creatures. Reduced atmospheric pressure would have allowed more efficient gas exchange for respiratory systems. The planet's distance from the Sun provided protection from solar flares and radiation that bombarded inner planets. Most intriguingly, Mars appears to have maintained stable climate conditions for much longer than early Earth. While our planet experienced several snowball Earth episodes and massive volcanic catastrophes, Mars enjoyed relatively gentle climate variations during its habitable period. This stability might have given evolution more time to produce complex organisms and potentially intelligence. The planet's two small moons, Phobos and Deimos, create unique tidal patterns that differ dramatically from Earth's single large moon. These complex tidal cycles might have provided additional energy sources for early life and created diverse ecological niches that could support rapid evolution toward intelligence. Recent discoveries of subsurface water, ice, and possible liquid water reservoirs suggest Mars might have remained partially habitable even after surface conditions deteriorated. Underground ecosystems could have provided refuge for organisms as the planet's atmosphere gradually escaped to space. Advanced species might have developed subterranean civilizations to survive the changing surface environment. The timing of Mars's decline coincides with several dramatic events in the inner solar system. Asteroid bombardment increased significantly around 3.8 billion years ago during a period called the Late Heavy Bombardment. Multiple impacts could have stripped away Mars's atmosphere, while simultaneously delivering water and organic compounds that jump-started life. Some impact craters on Mars show unusual characteristics that don't match typical asteroid collisions. Circular formations with raised rims and central peaks appear in clusters that suggest coordinated impacts rather than random bombardment. Alternative explanations invoke volcanic activity or tectonic processes, but the crater patterns don't match these natural mechanisms either. The loss of Mars's magnetic field remains poorly understood. Planetary magnetic fields require molten metallic cores with active circulation patterns. Mars apparently lost its magnetic field quite suddenly around 4 billion years ago, leaving the planet vulnerable to solar wind erosion that gradually stripped away its atmosphere. But magnetic field loss doesn't necessarily happen quickly through natural processes. Earth's magnetic field has reversed multiple times throughout geological history without causing permanent atmospheric loss. The rapid disappearance of Mars's magnetic protection suggests either catastrophic core cooling or external interference that disrupted the planet's internal dynamics. If intelligent life did evolve on ancient Mars, their fate offers sobering lessons about planetary survival. Even advanced civilizations might prove helpless against global environmental collapse or catastrophic events beyond their control. The red planet might represent not a failed world, but rather a cosmic crime scene preserving evidence of intelligence that couldn't save itself. The search for life on Mars continues, but we might be looking for the wrong kinds of evidence in the wrong places. Before Venus became a hellscape hot enough to melt lead, it might have been the most beautiful planet in the solar system. For nearly 2 billion years, Venus likely had oceans, moderate temperatures, and atmospheric conditions that could have supported not just life, but potentially advanced civilizations that thrived in a paradise we can barely imagine. Computer climate models reveal that ancient Venus probably maintained liquid water oceans until as recently as 700 million years ago. During this period, the planet received about 70% more solar energy than Earth, but a thicker atmosphere and global cloud cover could have reflected enough sunlight to maintain temperatures suitable for life. Ocean currents would have distributed heat around the planet, creating stable climate zones. The planet's extremely slow rotation, taking 243 Earth days to complete one turn, would have created unique weather patterns unlike anything on Earth. Massive atmospheric circulation cells would have transferred heat from the day side to the night side, preventing extreme temperature differences. This could have created vast temperate zones where liquid water remained stable for millions of years. Venus's lack of a large moon means no significant tides, but the planet's dense atmosphere would have created powerful wind patterns that could serve similar functions for driving chemical cycles and energy distribution. Atmospheric tides caused by solar heating might have provided regular energy sources for any evolving life forms. The planet's volcanic activity during this period would have provided essential minerals and chemicals needed for life. while also releasing water vapor and carbon dioxide that maintained greenhouse warming. Unlike the catastrophic volcanism that later destroyed Venus's habitability, early volcanic activity appears to have been more moderate and conducive to maintaining stable environmental conditions. Recent atmospheric analysis by space probes has detected phosphine gas in Venus's upper atmosphere. On Earth, phosphine is primarily produced by biological processes, though some geological sources exist. The concentrations detected on Venus exceed what known non-biological processes could produce, suggesting possible microbial life still surviving in the planet's acid clouds. But the phosphine discovery raises intriguing questions about Venus's biological history. If simple microbes can survive in the planet's current harsh upper atmosphere, what kinds of life might have flourished when Venus had oceans and moderate surface temperatures? Advanced ecosystems could have evolved during the planet's billions of years of habitability. The transformation from paradise to hell happened relatively quickly in geological terms. Runaway greenhouse warming triggered by volcanic outgassing gradually increased surface temperatures until the oceans boiled away completely. Water vapor in the upper atmosphere was broken down by solar radiation, and hydrogen escaped to space, while oxygen reacted with surface minerals. This runaway greenhouse process would have taken thousands or millions of years to complete, potentially giving any existing civilizations time to recognize the threat and develop countermeasures. Advanced species might have attempted geoengineering projects to reflect sunlight, remove atmospheric carbon dioxide, or migrate to orbital habitats. Evidence of such attempts might still exist in Venus's geological record, hidden beneath the planet's thick atmosphere and extreme surface conditions. Unusual mineral distributions, artificial structures, or technological artifacts could remain preserved under the planet's relatively young surface, which appears to have been completely resurfaced by volcanic activity within the past 500 million years. The Soviet Venera landers that successfully reached Venus's surface in the 1970s and 80s transmitted images showing flat landscapes covered with volcanic rocks, but the extreme conditions limited mission duration to less than 2 hours, providing only tiny glimpses of the planet's surface features. Future missions with advanced heat-resistant technology might reveal more about Venus's hidden history. Subsurface drilling could uncover layers that preserve evidence from the planet's habitable period. Radar mapping from orbit has already identified unusual surface features that don't match typical volcanic formations. If Venus once hosted advanced civilizations, their extinction offers a stark warning about the dangers of uncontrolled climate change. Even technological species might prove powerless against planetary-scale environmental collapse. The Paradise Planet became a cautionary tale written in sulfuric acid and molten stone. 2.4 billion years ago, Earth's atmosphere filled with a deadly poison that killed nearly all life on the planet. Oxygen, now essential for complex life, was originally a toxic waste product that triggered the first mass extinction event. But some organisms not only survived this catastrophe, they learned to harness the poison as an energy source and might have developed the first primitive technologies. Before the Great Oxidation Event, Earth's atmosphere contained virtually no free oxygen. Early life forms were anaerobic bacteria that thrived in oceans rich with dissolved iron and sulfur compounds. These ancient ecosystems were incredibly diverse, with organisms that could derive energy from sunlight, chemicals, and even radioactive decay. Then cyanobacteria evolved photosynthesis and began pumping oxygen into the atmosphere as a waste product. For these ancient bacteria, oxygen was simply chemical garbage to be discarded. But for most other life forms, oxygen was a corrosive poison that destroyed cellular machinery and caused fatal chemical reactions. The transition took hundreds of millions of years, but its effects were catastrophic. Oxygen levels rose from virtually zero to nearly modern concentrations. The gas reacted with dissolved iron in the ocean, creating massive iron oxide deposits that we still mine today. Methane that had previously helped warm the planet was oxidized and destroyed, triggering severe ice ages. Most anaerobic species went extinct, but some survived by retreating to oxygen-free environments deep underground or in isolated chemical environments. Others evolved sophisticated biochemical mechanisms to neutralize oxygen's toxic effects. A few species learned to use oxygen as a powerful energy source, gaining enormous advantages over their anaerobic competitors. These oxygen-breathing survivors became the ancestors of all complex life on Earth. But the transition period might have seen more than just biochemical evolution. Some species could have developed primitive technologies to help them survive in the changing environment. Consider the challenges facing intelligent anaerobic organisms during the Great Oxidation Event. They needed to find or create oxygen-free environments. While the atmosphere became increasingly toxic, they required new energy sources. As traditional chemical cycles broke down, they had to develop protection against corrosive atmospheric gases. Some bacterial species today demonstrate remarkable engineering abilities that could scale up to technological applications. Magnetotactic bacteria create tiny internal compasses using precisely manufactured magnetite crystals. Other species build complex mineral structures with properties that rival modern material science. Biofilm-forming bacteria coordinate their activities across vast networks that function like primitive computer systems. Ancient species facing extinction-level threats might have developed collective responses that resembled technological solutions. Coordinated construction of underground refuge systems could have protected communities from atmospheric oxygen. Selective breeding programs might have accelerated evolution toward oxygen tolerance. Primitive metallurgy could have produced materials resistant to oxidative damage. The fossil record from this period is sparse because most organisms were microscopic and didn't preserve well. But some geological formations show evidence of large-scale coordinated biological activity that exceeds what simple bacterial communities typically produce. Massive stromatolite reefs appeared during this period, suggesting organisms were building complex structures for protection or resource concentration. Isotope signatures in rocks from the Great Oxidation Event show unusual patterns that don't match purely natural processes. Carbon ratios suggest massive organic matter decomposition occurred in controlled environments rather than through random environmental destruction. Some researchers propose these signatures indicate primitive agricultural or waste management systems. The survivors of the Great Oxidation eventually gave rise to all complex life on Earth, but they might not have been the first intelligent species to face planet-wide environmental catastrophe. Their success in navigating this crisis could have required collective intelligence and technological capabilities that we're only beginning to understand. The lessons from the Great Dying remain relevant today as humanity faces its own planet-wide environmental challenges. The key to survival might lie in learning from whichever species successfully adapted to Earth's first great environmental transformation. Whether that adaptation was purely biological or included technological elements might determine how we interpret our own chances for long-term survival. 540 million years ago, complex life forms suddenly appeared on Earth with a diversity and sophistication that defies evolutionary timescales. The Cambrian explosion produced creatures with advanced eyes, sophisticated hunting strategies, and defensive systems that seemed designed by intelligence rather than shaped by gradual natural selection. Recent discoveries suggest this evolutionary burst might have had hidden architects guiding its direction. Before the Cambrian period, life consisted mainly of simple bacteria, primitive algae, and basic multicellular organisms that barely moved or interacted with their environment. The fossil record shows relatively little change for billions of years. Then, in a geological instant, complex organisms appeared simultaneously around the world, with features that should have taken millions of years to evolve. Trilobites emerged with compound eyes containing hundreds of precisely aligned calcite lenses that provided sophisticated vision capabilities. Modern arthropods took millions of years to develop similar visual systems through gradual improvements. The mathematical precision required to design functional compound eyes suggests engineering principles rather than random evolutionary experimentation. Anomalocaris, one of the Cambrian's top predators, possessed flexible grasping arms with sophisticated hydraulic systems for capturing prey. Its body plan incorporated features from multiple animal groups that wouldn't appear together again for millions of years. The creature's combination of adaptations seems almost artificially assembled rather than naturally evolved. Hallucigenia walked on multiple pairs of spiny legs while defending itself with rows of protective spikes along its back. This bizarre anatomy served specific functional purposes, but required precise coordination between multiple organ systems. The probability of such complex integrated features appearing simultaneously through random mutation approaches zero. Even more puzzling, many Cambrian organisms possessed features that provided no apparent survival advantage in their ancient environments. Some species had sensory organs adapted for detecting chemicals that didn't exist in significant concentrations during the Cambrian period. Others developed defensive structures optimized against predation strategies that no known predators employed at the time. These anticipatory adaptations suggest organisms were evolving responses to future environmental conditions or threats that hadn't yet appeared. Natural selection can only respond to current selective pressures, not future challenges that haven't emerged yet. The presence of seemingly premature adaptations implies some form of directed evolution, guided by intelligence capable of predicting future ecological changes. Genetic analysis of modern animals reveals another anomaly from the Cambrian period. Most major animal body plans and developmental genetic toolkits appeared simultaneously during this brief evolutionary window. The complex genetic machinery required for building eyes, brains, and limbs seems to have been invented all at once rather than gradually assembled over millions of years. The Hox genes that control body plan development in all complex animals show evidence of rapid coordinated changes during the Cambrian period. These master control genes regulate the expression of hundreds of other genes and determine fundamental aspects of animal architecture. Simultaneous changes in multiple Hox genes could theoretically be directed by some form of external genetic engineering. Some researchers propose that horizontal gene transfer between species might have accelerated Cambrian evolution. Bacteria routinely exchange genetic material, allowing rapid spread of beneficial mutations across entire populations. If early complex organisms retained some capacity for horizontal gene transfer, evolutionary innovations could have been shared between species rather than evolving independently. But horizontal gene transfer requires sophisticated molecular machinery for incorporating foreign DNA without disrupting essential cellular processes. The precision required to successfully integrate complex genetic modifications suggests advanced biotechnology rather than natural bacterial processes. Alternative explanations invoke environmental changes that created new selective pressures during the Cambrian period. Rising oxygen levels, changing ocean chemistry, and predator-prey arms races could have accelerated evolutionary innovation. But the speed and coordination of changes still exceed what these environmental factors should have produced. The Cambrian explosion might represent evidence of the first biological engineering project on Earth. Whether guided by intelligence from evolving organisms themselves or external influences we don't understand, this evolutionary burst demonstrates that complex life can be directed and accelerated far beyond natural rates. The architects of the Cambrian explosion left their signature written in the genes of every complex organism on Earth. Embedded in rocks millions of years old, strange objects tell impossible stories about Earth's ancient past. These out-of-place artifacts, dismissed by mainstream science as hoaxes or misidentifications, continue to emerge from coal mines, quarries, and archaeological sites around the world. While most can be explained through natural processes or contamination, a few remain genuinely mysterious and challenge our understanding of geological time. In 1844, Scottish physicist Sir David Brewster reported finding a metal nail embedded in sandstone from a quarry near Glasgow. The rock formation dated to approximately 400 million years old, long before complex life existed on land. Chemical analysis revealed the nail was composed of iron with traces of nickel, consistent with manufactured metal rather than natural iron ore. Similar discoveries include a gold chain found inside coal dated to 300 million years old, a bell-shaped vessel recovered from solid rock in Massachusetts, and numerous metal spheres extracted from Precambrian formations in South Africa. Each discovery follows the same pattern: manufactured objects found in geological contexts that predate human civilization by hundreds of millions of years. Skeptics correctly point out that most alleged out-of-place artifacts can be explained through contamination, misidentification, or fraud. Modern objects can penetrate ancient rock through fractures, root channels, or human disturbance. Natural minerals can form shapes that resemble manufactured items. Hoaxers have incentives to create fake discoveries that attract publicity and potential financial rewards. But a few cases resist easy debunking. The Wolfsegg iron, discovered in Austria in 1885, remains one of the most thoroughly documented anomalous artifacts. The cube-shaped object was found embedded in brown coal dating to 20 million years old. Multiple expert analyses confirmed the object's artificial origin and ruled out natural formation processes. The artifact weighs 1.73 lb and measures roughly 2.6 in on each side. Deep grooves cut into its surface form precise geometric patterns that don't occur in nature. X-ray analysis reveals internal structure consistent with cast metal construction. Carbon dating of surrounding coal confirms the deposit's ancient age. Most intriguingly, the object's composition includes materials that don't occur naturally together. The primary metal appears to be iron, but contains unusual trace elements in proportions that suggest artificial alloy production. No known geological process could create this specific combination of metals in the observed ratios. The Antikythera mechanism, while not embedded in ancient rock, demonstrates how sophisticated technology can be lost and forgotten for thousands of years. This ancient Greek device contained bronze gear systems sophisticated enough to calculate planetary positions and predict eclipses. Its discovery in 1901 revolutionized understanding of ancient technological capabilities. If Greeks could build mechanical computers 2,000 years ago, what technologies might civilizations have developed during Earth's 4 billion-year history of life? The fossilization process preserves only tiny fractions of ancient organisms under specific conditions. Technological artifacts would be even less likely to survive geological processes that recycle most surface materials over millions of years. Modern industrial archaeology demonstrates how quickly technological evidence disappears. Abandoned factories rust away within decades. Electronic devices corrode into unrecognizable fragments. Even massive concrete structures crack and crumble when exposed to natural weathering processes. But certain materials could theoretically survive for millions of years under the right conditions. Metallic glass maintains its structure longer than conventional metals. Some ceramics resist chemical breakdown for geological time periods. Crystalline materials can preserve microscopic details across enormous time spans. The search for ancient technological artifacts faces fundamental challenges. We don't know what materials ancient civilizations might have used, or what their technologies would look like after millions of years of alteration. Archaeological techniques designed for finding human artifacts might miss evidence of non-human intelligence entirely. Perhaps most importantly, extraordinary claims require extraordinary evidence. While out-of-place artifacts deserve scientific investigation, proving their authenticity and ancient origin requires rigorous analysis that meets the highest standards of evidence. Until such proof emerges, these mysterious objects remain tantalizing hints of possibilities that challenge our assumptions about Earth's deep history. Frank Drake's famous equation promised to calculate the number of communicating civilizations in our galaxy, but 70 years of searching has revealed a terrifying mathematical reality. The numbers that should guarantee cosmic neighbors instead predict cosmic loneliness. When we plug realistic values into the Drake equation, we discover that intelligent life might be so extraordinarily rare that we could be alone in not just our galaxy, but the entire observable universe. The Drake equation multiplies together 7 factors: the rate of star formation, the fraction of stars with planets, the number of planets per star in habitable zones, the fraction that develop life, the fraction that evolve intelligence, the fraction that develop technology, and the length of time civilizations remain detectable. Each factor seems reasonable in isolation, but their combined effect creates mathematical devastation. Start with star formation rates in the Milky Way. Roughly 7 new stars form each year, and most develop planetary systems. Recent exoplanet surveys suggest nearly every star hosts planets, with many systems containing worlds in habitable zones where liquid water could exist. These early factors in the Drake equation generate optimistic numbers suggesting millions of potentially habitable worlds. But the biological factors introduce crushing limitations. The probability that chemistry becomes biology remains completely unknown despite decades of research into the origin of life. Laboratory experiments have produced some organic compounds under simulated early Earth conditions, but creating self-replicating systems that qualify as living remains far beyond current capabilities. Even if simple life emerges readily, the transition to complex cells appears incredibly difficult. Earth required over 2 billion years to evolve nucleated cells from bacterial ancestors. This enormous delay suggests fundamental barriers that might prevent most biospheres from ever developing complex organisms. Intelligence represents another catastrophic bottleneck. Despite hundreds of millions of years of evolution producing countless species on Earth, only one lineage developed technology capable of interstellar communication. The cognitive abilities required for science and engineering might emerge so rarely that most planets with complex life never produce technological civilizations. The final factor, civilization longevity, introduces the most disturbing possibilities. If technological species systematically destroy themselves within centuries or millennia of discovering science, then the universe could be littered with the ruins of countless civilizations that existed too briefly to establish contact with others. Recent attempts to estimate realistic values for Drake equation parameters produce sobering results. Conservative calculations suggest that fewer than one technological civilization per galaxy exists at any given time. More pessimistic estimates indicate that civilizations might be separated by millions of galaxies and billions of years. The Fermi paradox crystallizes this mathematical nightmare. If intelligent life should be common, where is everybody? The silence from space doesn't necessarily mean we're alone, but it suggests that whatever processes create detectable civilizations operate on time and distance scales that make contact virtually impossible. Anders Sandberg's recent analysis used advanced statistical methods to estimate probability distributions for unknown Drake equation parameters. His calculations indicate that the probability of another contemporary civilization existing in our galaxy might be less than 1 in 10 billion. The probability of civilizations existing in our local galactic cluster approaches 0. These results don't prove we're alone, but they demonstrate that cosmic loneliness represents the most likely scenario given our current understanding of astronomy and biology. The absence of alien signals becomes not a mystery requiring explanation, but rather the expected result of universal mathematical realities. The implications for humanity are profound. If we represent the only known intelligence in the observable universe, our survival becomes a cosmic imperative. The extinction of human civilization might eliminate the only consciousness capable of understanding and appreciating the universe's magnificent complexity. But the mathematics also offer hope. If intelligence is truly rare, then Earth's biosphere represents something precious beyond imagination. Every species, every ecosystem, and every moment of cosmic awareness becomes infinitely valuable in a universe that might otherwise remain forever unconscious. The search for extraterrestrial intelligence continues, but the Drake equation suggests we might be searching for something that exists only in our dreams of cosmic companionship. In 1950, physicist Enrico Fermi asked a question that still keeps scientists awake at night. If the universe should be teeming with intelligent life, where is everybody? This simple question, now called the Fermi paradox, exposes a terrifying gap between our expectations of cosmic abundance and the reality of absolute silence from space. Numbers should overwhelm us with alien voices. Our galaxy contains roughly 400 billion stars, most with planetary systems. Conservative estimates suggest billions of planets exist in habitable zones where liquid water could support life. Even if intelligence emerges rarely, the sheer scale of opportunities should produce detectable civilizations somewhere in our cosmic neighborhood. Time amplifies these probabilities to near certainty. The Milky Way has been forming stars and planets for over 10 billion years. Older civilizations should have had enormous head starts on technological development. Advanced species with even modest expansion capabilities could have colonized entire sectors of the galaxy multiple times over. Yet, our most sensitive radio telescopes detect nothing but cosmic static. Projects like SETI have monitored millions of star systems across thousands of frequency channels without finding a single artificial signal. Optical searches scan for laser communications or megastructure signatures that would indicate massive engineering projects. Infrared surveys hunt for waste heat from energy consumption that any expanding civilization would produce. The silence becomes more mysterious when we consider how detectable technological civilizations should become. Radio and television broadcasts leak into space, creating expanding spheres of artificial signals that travel at light speed. Nuclear weapons testing produces distinctive gamma-ray signatures visible across interstellar distances. Industrial pollution alters atmospheric chemistry in ways that space telescopes could detect around nearby stars. Even civilizations trying to remain hidden would struggle to conceal their existence completely. Large-scale energy consumption generates waste heat that appears as infrared emissions. Interstellar spacecraft require enormous amounts of energy for propulsion, creating detectable exhaust signatures. Megastructures like Dyson spheres around stars would produce characteristic changes in stellar brightness patterns. The paradox deepens when we examine how quickly intelligence could spread across the galaxy. Chemical rockets could carry robotic probes to nearby star systems within thousands of years. Self-replicating machines could establish colonies that build more probes, creating exponential expansion waves. Even at modest speeds, such expansion could reach every star system in the galaxy within a few million years. Some proposed solutions invoke the zoo hypothesis, suggesting advanced civilizations deliberately avoid contact with primitive species like humanity. Others propose that intelligence consistently destroys itself through warfare, environmental collapse, or technological disasters before achieving interstellar capabilities. more disturbing possibilities suggest that advanced civilizations transcend physical reality through technological singularities that make them undetectable to primitive observers. They might upload their consciousness into digital realities, retreat into microscopic computational substrates, or discover physics that allows escape from our observable universe entirely. The Great Filter hypothesis offers the most sobering explanation. Something eliminates nearly all intelligent species before they can establish permanent interstellar presence. This filter could operate at any stage of development, from the origin of life to advanced technological phases that lie ahead of our current capabilities. If the filter lies behind us, we might be among the extremely rare species that successfully navigated early evolutionary challenges. If it lies ahead, humanity faces the same barriers that eliminated countless previous civilizations throughout cosmic history. The silence from space might not represent absence of intelligence, but rather evidence of universal evolutionary bottlenecks that we have yet to encounter. 7 meters down in the deepest ocean trenches where sunlight has never penetrated and pressure would crush submarines like tin cans, strange geometric formations appear on sonar maps that don't match any known geological process. These underwater features, hidden beneath miles of water and sediment, might preserve evidence of civilizations that thrived when the ocean floor was dry land millions of years ago. The Mariana Trench, Earth's deepest point, plunges over 36,000 ft below sea level into a world more alien than the surface of Mars. Recent deep-sea mapping reveals rectangular formations, perfectly straight lines, and circular structures arranged in patterns that resemble urban planning more than natural geology. These features span miles in diameter and show geometric precision that defies explanation through conventional geological processes. Tectonic activity constantly recycles ocean floor, making it impossible for surface features to survive more than 200 million years. But some deep ocean formations appear much older based on sediment analysis and magnetic signatures. Layers of accumulated debris bury these ancient structures under thousands of feet of mud, creating time capsules that preserve whatever existed before the current ocean floor formed. The most intriguing discoveries come from areas where underwater mountain ranges show evidence of having been above sea level in the distant past. Continental drift and sea level changes mean that current ocean basins once hosted dry land environments where complex ecosystems and potentially civilizations could have developed over millions of years. Advanced sonar mapping technology reveals details that weren't visible to earlier ocean exploration efforts. Three-dimensional imaging shows structures with internal chambers, connecting tunnels and architectural features that would be functional for large organisms or intelligent beings. Some formations contain what appear to be deliberate geometric patterns carved into solid rock. The Bimini Road near the Bahamas demonstrates how underwater structures can spark controversy about ancient civilizations. This limestone formation consists of rectangular blocks arranged in linear patterns that some researchers interpret as artificial construction. While most geologists explain the feature through natural limestone fracturing, the precise geometry and apparent tool marks on some blocks remain unexplained. Deep-sea drilling projects occasionally recover materials that don't match expected sediment compositions. Strange metallic fragments, unusual mineral concentrations, and organic compounds that don't fit known biological signatures suggest the ocean floor might contain artifacts from ancient surface environments. Hydrothermal vents at the bottom of ocean trenches support complex ecosystems that survive without sunlight by deriving energy from chemical processes. These environments demonstrate that advanced life forms can thrive in extreme conditions that might have existed around ancient underwater cities. Some vent communities show organization, patterns that exceed what simple chemical gradients should produce. The preservation potential in deep ocean environments exceeds that of surface locations by enormous factors. Cold temperatures, low oxygen levels, and protection from weather create conditions where organic materials and manufactured objects could survive for millions of years. Even delicate structures might remain intact if buried quickly by sediment flows. Current deep-sea exploration technology can only sample tiny fractions of ocean floor terrain. The deepest trenches remain largely unmapped at high resolution, and most underwater geological surveys focus on relatively shallow continental shelf areas. Vast regions of deep ocean floor have never been examined for possible artificial structures. Robotic submersibles capable of reaching maximum ocean depths operate for only a few hours per mission and can explore areas measured in square miles rather than the millions of square miles of deep ocean floor that exist. The probability of randomly encountering ancient artificial structures remains vanishingly small given current exploration capabilities, but systematic searches targeting geometrically unusual formations could reveal evidence that random exploration would miss. Artificial intelligence analysis of sonar data might identify patterns that human interpreters overlook. Advanced drilling techniques could sample suspected artificial structures without destroying them. The deep ocean represents Earth's largest unexplored frontier, and it might hold the key to understanding whether previous civilizations left traces that we simply haven't found yet. Beneath Antarctica's ice sheets, 2 meters thick and millions of years old, satellite mapping has revealed massive structures that defy explanation. These formations, hidden under frozen water that hasn't melted since before humans evolved, might preserve evidence of ancient civilizations that thrived when Antarctica was a temperate continent covered with forests and rivers. Ground-penetrating radar and satellite imagery show geometric patterns buried under the ice that don't match any known geological processes. Straight lines extend for dozens of miles. Perfect circles span several miles in diameter, and rectangular formations arranged in grid patterns suggest urban planning rather than natural landscape features. These structures remain frozen in time, protected from erosion and weathering that would have destroyed similar evidence elsewhere on Earth. Antarctica wasn't always a frozen wasteland. 50 million years ago, the continent hosted temperate forests with palm trees and complex ecosystems that supported diverse wildlife. Cold deposits and fossil evidence prove that warm climate conditions persisted for millions of years before the continent drifted to its current polar position and became locked in ice. During this warm period, Antarctica would have been ideal for supporting advanced life forms and potentially civilizations. The continent's isolation from other land masses could have allowed unique evolutionary experiments to develop without interference from competing species. Large land area and abundant resources would have supported substantial populations over long periods. Recent ice core drilling has revealed anomalous materials embedded in ice layers that formed millions of years ago. Metallic fragments, unusual mineral concentrations, and organic compounds that don't match known Antarctic organisms suggest the ice sheets have preserved materials from ancient surface environments that existed before glaciation. Lake Vostok, buried under 2 miles of ice, represents one of Antarctica's most mysterious features. This subglacial lake contains liquid water that has been isolated from surface conditions for potentially millions of years. Initial sampling revealed microbial life forms that don't match any known species, suggesting unique ecosystems have survived in isolation beneath the ice. But Lake Vostok also shows geometric features visible on satellite maps that don't match typical lake formations. The shoreline includes straight segments and angular features that appear artificial rather than natural. Some researchers suggest these features result from unusual geological processes, while others propose more intriguing explanations. The Piri-Reis map drawn in 1513 by Ottoman Admiral Piri Reis shows detailed coastlines of Antarctica without ice coverage. This map predates official Antarctic discovery by 300 years and depicts geographical features that weren't confirmed until modern satellite mapping. The accuracy suggests access to ancient knowledge about Antarctica's preglacial geography. Advanced ice-penetrating radar systems reveal internal structure within the ice sheets that includes cavities, tunnels, and chamber-like formations. While most of these features probably result from natural ice flow and melting processes, some show geometric regularity that doesn't match known glacial formations. Global warming threatens to expose Antarctic secrets that have remained hidden for millions of years. Accelerating ice melt could reveal surface features that have been preserved under ice since before the current ice age began. But the same melting processes might destroy fragile evidence before it can be properly studied and documented. International treaties currently restrict Antarctic exploration and require extensive permits for scientific research. These limitations prevent the kind of systematic archaeological investigation that would be needed to determine whether anomalous features represent natural formations or something more significant. Private exploration efforts face even greater restrictions and technical challenges. The extreme conditions, remote location, and enormous expenses involved in Antarctic operations limit research to well-funded government and international scientific programs that prioritize climate and biological research over archaeological investigations. Time may be running out to investigate Antarctica's buried secrets. Climate change accelerates ice loss, while international tensions complicate research cooperation. Whatever lies beneath Antarctica's ice sheets might remain hidden until melting ice reveals it to a world unprepared for the discovery. The frozen continent guards its mysteries, but the ice won't last forever. The Moon's preserved history. Earth's moon preserves 4 billion years of cosmic history on its airless, weatherless surface, where nothing erodes and every impact crater tells a story. This pristine archaeological record may contain evidence of ancient Earth civilizations, locked in lunar rocks and buried beneath dust accumulated over geological ages. Unlike Earth, where weather, water, and geological activity destroy evidence within millions of years, the Moon's surface remains virtually unchanged for billions of years. Footprints left by Apollo astronauts 50 years ago still look fresh today. Anything reaching the Moon's surface during Earth's 4 billion-year history of life would remain perfectly preserved. Large asteroid impacts on Earth regularly blast material into space with enough velocity to reach the Moon. Simulations show these impacts launch millions of tons of terrestrial rock into lunar orbit, where gravitational capture spreads this material across the Moon's surface. Every major catastrophe in Earth's history is likely preserved somewhere in the lunar record. The Moon therefore contains samples of Earth's surface from every era, including times when advanced life or civilizations may have existed. Organic molecules, manufactured materials, and artifacts could survive indefinitely in the Moon's vacuum, shielded from chemical reactions and decay that erase evidence on Earth. Apollo samples confirm this. Some contain isotope ratios matching Earth's mantle composition, proving terrestrial material reached the Moon. The discovery of water ice in permanently shadowed craters shows even volatile compounds can survive millions of years in the right conditions. Anomalies on the lunar surface. High-resolution orbital images reveal unusual features inconsistent with typical craters or volcanic formations. Geometric structures, straight lines, and patterns suggesting artificial origin appear in images from multiple missions. While most likely natural, some remain unexplained. The lunar far side, permanently hidden from Earth, contains the oldest and most pristine features in the solar system. This makes it the best location to search for preserved terrestrial evidence. China's Chang'e missions began exploring the far side, but coverage is limited to small landing sites. Comprehensive archaeological surveys would require orbital mapping, specifically targeting anomalies. Apollo brought back less than 9 pounds of material from 6 nearside sites. This tiny sample barely scratches the surface of lunar terrain. Statistical analysis suggests that evidence of ancient civilizations could exist, but with extremely low detection probability through random sampling. Future lunar missions by governments and private companies may change this. Permanent bases would allow systematic archaeological surveys, while advanced drilling could access subsurface layers preserving older material. Mining operations might inadvertently uncover preserved artifacts while extracting resources. Legal and preservation challenges. International space law has no framework for archaeological preservation of extraterrestrial sites. Resource competition could destroy irreplaceable evidence before investigation. Still, the Moon's archaeological potential remains untapped. 4 billion years of Earth's history lie preserved in lunar dust and rocks, waiting for the right missions to unlock them. The Moon remembers everything and may finally be ready to tell us. Earth's erasure of civilizations. Earth functions as a massive recycling system, systematically destroying nearly all traces of surface civilizations. Geological forces, erosion, burial, glaciation, volcanism, chemical weathering, biology, and climate changes ensure that even advanced societies leave little evidence after a few million years. Tectonics, plate drift crushes, buries, and subducts surface features into the mantle. Ocean floors recycle within 200 million years. The oldest ocean crust today is only that age. Erosion, wind, water, and chemical weathering wear down even massive stone structures. The Egyptian pyramids, just 4,000 years old, already show damage. Mountains once taller than the Himalayas are now gentle hills. Sedimentation, rivers bury features under thousands of feet of deposits, compressing them into stone. Glaciation, ice sheets scour landscapes, grinding rock into powder and redistributing debris. Volcanism, lava flows and ash bury and chemically alter landscapes. Chemical and biological decay, metals corrode, ceramics decompose, and organisms or structures rot. Even concrete is overtaken by nature within decades. Climate shifts, sea levels rise and fall, flooding coasts. Freeze-thaw cycles fracture stone. Rainfall changes accelerate erosion. Together, these processes erase evidence on scales that dwarf human history. The scale of time. Civilization spans about 10,000 years. Industrial technology covers just 200. Recorded history is less than 0.002% of the time since complex life began. If Earth's history were a single year, human civilization would occupy only the last few seconds before midnight on December 31st. This perspective reveals why finding ancient civilizations is so unlikely. Civilizations may have arisen and vanished without overlapping in time or leaving detectable traces. Preservation odds worsen over millions of years. Soft tissues decay in decades. Wood rots in centuries. Metals corrode in thousands of years. Stone structures crumble in millions. Even fossils, our best preserved evidence, are rare, requiring precise conditions. Most species left no trace at all. Artifacts face even worse odds. Plastics, electronics, and complex machinery break down chemically and structurally. The search for ancient technology is further hindered by assumptions that other civilizations used materials or methods similar to ours. But intelligence that evolved millions of years ago might have developed completely different technological solutions. Their artifacts might not be recognizable as artificial constructions to archaeologists trained to find human-made objects. Even more fundamentally, the definition of what constitutes evidence of intelligence becomes problematic over geological timescales. Modern humans can recognize ancient human artifacts because we understand human behavior, needs, and capabilities, but intelligence that evolved independently from humans might have produced technologies, art, and architecture that we couldn't distinguish from natural phenomena. Statistical analysis reveals the detection challenges. Mathematically, if ancient civilizations existed for periods similar to human technological development, about 10,000 years, and occurred randomly throughout Earth's 4 billion-year history, the probability of finding preserved evidence depends on preservation rates and search coverage that make detection highly unlikely. Current archaeological and geological survey methods examine tiny fractions of Earth's surface and subsurface environments. Most excavation projects focus on sites where human artifacts are expected to exist based on historical records or surface indicators. Systematic searches for non-human artifacts would require completely different methodological approaches. The timescales also create dating challenges that could make ancient artifacts appear natural, even if discovered. Radiometric dating methods used for geological specimens operate with error margins measured in millions of years. Determining whether unusual objects are artificial or natural becomes nearly impossible when dealing with specimens older than several million years. But perhaps most significantly, geological timescales mean that multiple civilizations could have existed during periods when Earth's surface geography, climate, and even atmospheric composition were dramatically different from current conditions. These ancient worlds might have supported forms of intelligence and technology that would be unrecognizable to modern observers. The enemy isn't just time, but the fundamental assumption that intelligence leaves traces detectable across geological eras. While most evidence of ancient civilizations disappears within thousands of years, certain advanced materials could theoretically survive for tens of millions of years under the right conditions. Understanding which substances resist geological destruction reveals what kinds of artifacts we should be searching for and where they might be hiding in Earth's deep history. Diamond represents the ultimate in material durability. This crystalline form of carbon resists chemical weathering, maintains structural integrity under extreme pressure and temperature, and remains stable for billions of years. Industrial diamonds used in cutting tools could survive virtually any geological process, short of direct exposure to temperatures above 3,000 degrees F. Advanced ceramics demonstrate remarkable longevity under harsh conditions. Silicon carbide, titanium carbide, and other engineering ceramics resist corrosion, weathering, and chemical breakdown far longer than metals or organic materials. These substances could maintain recognizable structures for millions of years if protected from mechanical abrasion and extreme temperature cycling. Metallic glasses, created through rapid cooling of molten metal alloys, possess unusual properties that make them resistant to normal corrosion processes. Unlike crystalline metals that contain grain boundaries where chemical reactions initiate, metallic glasses have homogeneous atomic structures that resist oxidation and other degradation mechanisms. Some synthetic polymers designed for extreme environment applications could survive geological timescales under specific conditions. ultra-high molecular weight polyethylene, perfluorinated plastics, and other engineered materials maintain their properties in environments that destroy conventional plastics within decades. Crystalline quartz and other silicate minerals demonstrate that complex artificial structures can survive for hundreds of millions of years. Carved quartz artifacts would be virtually indistinguishable from natural crystal formations after geological timescales, but microscopic examination might reveal tool marks or geometric precision that indicates artificial origin. Advanced composites combining multiple resistant materials could achieve even greater longevity. Carbon fiber-reinforced ceramics, metal matrix composites, and other engineered materials designed for aerospace applications combine the best properties of different substance types. Such composites might retain recognizable artificial characteristics for millions of years. Nanotechnology introduces possibilities for materials with unprecedented durability. Diamond-like carbon coatings, fairing structures, and other nanoscale materials could theoretically maintain their properties indefinitely under appropriate storage conditions. Molecular-scale manufacturing might produce artifacts that survive geological recycling processes. But material durability alone doesn't guarantee preservation. Even the most resistant substances face destruction through mechanical processes like tectonic crushing, thermal cycling, and erosive transport. Surviving geological timescales requires not just durable materials, but also favorable environmental conditions that minimize destructive forces. Underground environments offer the best preservation potential. Deep burial protects materials from oxidation, temperature cycling, and mechanical weathering, while maintaining relatively stable chemical conditions. Caves, deep sedimentary layers, and other subsurface locations could preserve artifacts for millions of years. Certain surface locations also provide exceptional preservation conditions. Desert environments with minimal rainfall limit chemical weathering processes. Polar regions maintain low temperatures that slow chemical reaction rates. Volcanic regions might rapidly bury materials in protective lava or ash layers. Aquatic environments present mixed preservation opportunities. Underwater locations protect materials from atmospheric oxygen and temperature fluctuations, but exposure to dissolved minerals and biological activity can accelerate some types of degradation. Deep ocean environments offer better preservation than shallow water locations. The key insight is that ancient civilizations might have deliberately designed their most important artifacts for extreme longevity. Messages intended for future discovery could have been constructed using the most durable available materials and placed in locations selected for optimal preservation conditions. Archaeological searches should focus on these resistant materials and favorable preservation environments rather than looking for conventional artifacts in typical archaeological contexts. Ancient intelligence might have understood geological timescales better than we assume and taken steps to ensure their legacy would survive. The materials exist to preserve evidence across geological time. The question becomes whether ancient civilizations were sophisticated enough to use them deliberately and clever enough to hide their messages where future intelligence would eventually find them. But even the most durable materials face ultimate destruction through processes that operate over hundreds of millions of years. Every civilization that harnesses large amounts of energy leaves distinctive signatures locked in the geological record, like fossilized fingerprints of industrial activity. These energy markers persist in sedimentary layers, ice cores, and rock formations long after the civilizations themselves have disappeared, creating a hidden archive of ancient technological activity that we're only beginning to learn how to read. Burning fossil fuels creates characteristic carbon isotope ratios that differ measurably from carbon cycled through natural biological processes. Coal, oil, and natural gas contain carbon depleted in the heavier carbon-13 isotope because they formed from ancient organic matter through specific geological processes. When burned, these fuels release carbon dioxide with distinctive isotopic signatures that remain detectable in atmospheric records for thousands of years. Industrial-scale metal smelting leaves permanent traces in the form of pollution signatures preserved in ice cores, lake sediments, and soil layers. Lead from ancient Roman mining operations remains detectable in Greenland ice cores 2,000 years later. Copper, tin, and iron processing produces characteristic patterns of heavy metal contamination that persist in the geological record longer than the civilizations that created them. Large-scale construction projects alter local geological formations in ways that remain visible for millions of years. Quarrying operations create distinctive excavation patterns and waste rock distributions. Dam construction changes river sediment patterns both upstream and downstream from the construction site. Urban development compacts soils and alters local drainage patterns in ways that fossilize into permanent geological features. Nuclear technology produces the most persistent energy signatures of any human activity. Uranium enrichment, plutonium production, and nuclear weapons testing create radioactive isotopes that don't occur naturally in the observed concentrations. These artificial isotopes have half-lives ranging from years to millions of years, ensuring their signatures remain detectable long after the technology that created them has been forgotten. The Trinity nuclear test in 1945 created a layer of radioactive glass called trinitite that preserves the exact moment when humans first harnessed nuclear energy. Similar signatures from ancient nuclear technology could exist in the geological record if previous civilizations developed atomic energy millions of years ago. Atmospheric nuclear testing between 1945 and 1963 created a global radiation spike that appears in tree rings, ice cores, and sediment layers around the world. This radiation signature represents a permanent marker that will remain detectable for thousands of years, creating a clear boundary in the geological record that marks the beginning of the nuclear age. But nuclear signatures also illustrate how energy markers can disappear over geological time. Radioactive isotopes decay predictably, and most fission products become undetectable within thousands to millions of years. Only isotopes with extremely long half-lives would remain detectable after tens of millions of years, and these are typically produced in smaller quantities. Chemical pollution from industrial processes creates another category of persistent energy signatures. Synthetic chemicals that don't occur naturally remain detectable in environmental samples long after their production ceases. Some industrial compounds break down slowly and accumulate in sedimentary layers where they preserve records of manufacturing activity. Advanced energy technologies might produce signatures completely different from conventional fossil fuel or nuclear markers. Fusion power would create distinctive helium isotope ratios. Antimatter annihilation would produce characteristic gamma-ray signatures. Zero-point energy extraction or other exotic technologies could leave traces that we don't know how to recognize yet. The absence of expected energy signatures in the geological record might be as significant as their presence. If ancient civilizations developed clean energy technologies that produced minimal environmental impact, their energy consumption might remain invisible to current detection methods. Advanced civilizations might have been more environmentally responsible than modern humans. Climate engineering or terraforming activities would create massive energy signatures detectable for millions of years. Atmospheric modification, ocean chemistry changes, or large-scale ecosystem management would require energy expenditures comparable to natural geological processes and would leave correspondingly large traces in the geological record. Finding ancient energy signatures requires knowing what to look for and where to search. Current geological surveys focus on natural processes and aren't designed to detect artificial energy markers from unknown technologies. The Stone Archive of Ancient Energy use awaits proper investigation by researchers who understand what questions to ask. Just as biological evolution left fossils embedded in rock layers, technological civilizations should leave behind technofossils, preserved remnants of artificial materials, structures, and pollution that mark their existence in the geological record. The search for these technological artifacts represents a new field of archaeology that must peer millions of years into Earth's past using methods that haven't been invented yet. Conditions that rapidly bury organic materials in sediment prevent decay and allow mineralization. Technofossils would form through similar processes, but preserve evidence of intelligence rather than natural evolution. Manufacturing waste, construction materials, and pollution signatures could fossilize just as effectively as shells, bones, and plant matter. The Anthropocene represents Earth's first clearly recognizable technosyl layer. Human industrial activity has created distinctive geological signatures that will remain detectable for millions of years. Plastic particles, concrete foundations, metal artifacts, and radioactive isotopes mark a clear boundary in the geological record, where natural processes gave way to artificial modification of planetary systems. The current human technofossils might not represent the first such layer in Earth's geological history. Previous civilizations could have left similar signatures during earlier periods when conditions favored preservation of artificial materials. The challenge lies in recognizing technofossils from species that might have used completely different technologies and materials. Plastic pollution demonstrates how artificial materials can spread globally and become incorporated into geological formations. Microplastics now appear in ocean sediments, lake beds, and even remote mountain locations, where wind and water have carried them far from their origins. These synthetic polymers will remain detectable in rock layers for millions of years. Electronic waste creates another category of potential technofossils. Rare earth elements used in computer circuits, smartphones, and other devices become concentrated in landfills and electronic recycling facilities. These unusual elemental concentrations could remain detectable long after the devices themselves have degraded beyond recognition. Urban construction produces massive quantities of concrete, steel, and other artificial materials that alter local geology permanently. Cities create distinctive geological signatures through building foundations, utility tunnels, road surfaces, and buried infrastructure that would remain detectable even after surface structures have eroded away. Advanced materials used in aerospace and military applications might survive long enough to become recognizable technofossils. Titanium alloys, carbon fiber composites, and ceramic heat shields resist environmental degradation much longer than conventional materials. Future archaeologists might find fragments of spacecraft or aircraft embedded in rock formations millions of years from now. But technofossil detection faces enormous challenges that don't affect biological paleontology. We don't know what materials ancient civilizations might have used, or how their artifacts would appear after millions of years of alteration. Searching for unknown artificial materials requires completely different methodological approaches than traditional fossil hunting. Chemical analysis might provide the most reliable technofossil indicators. Artificial materials often contain elemental ratios that don't occur naturally or isotopic signatures that result from manufacturing processes. Mass spectrometry and other analytical techniques could identify synthetic compounds even when their original structures have been destroyed. Geometric patterns preserved in rock formations might indicate artificial origin even when material composition doesn't provide clear evidence. Perfect circles, straight lines, and mathematical relationships rarely occur in natural geological processes. Statistical analysis of geometric features could distinguish artificial construction from natural formation. Microscopic examination could reveal manufacturing traces invisible to normal archaeological investigation. Tool marks, crystalline structures, and molecular arrangements created by artificial processes might remain detectable at microscopic scales long after macroscopic features have disappeared. The search for technofossils requires interdisciplinary collaboration between geologists, archaeologists, material scientists, and other specialists who understand both natural geological processes and artificial material properties. Current academic structures don't support the kind of research programs needed for systematic technofossil investigation. But the potential rewards justify the methodological challenges. Discovering clear evidence of ancient technological civilizations would revolutionize our understanding of intelligence, evolution, and planetary history. It would also provide crucial data for predicting humanity's own long-term survival prospects. The technofossil record is waiting to be discovered, but we must first learn how to read the artificial signatures hidden in stone. Runaway climate change represents one of the most powerful mechanisms for destroying advanced civilizations, capable of eliminating even sophisticated technological societies within centuries or decades when planetary environmental systems cross critical tipping points and spiral beyond any possibility of control or recovery. Venus provides the ultimate example of runaway greenhouse collapse. 4 billion years ago, the planet probably had oceans and temperate conditions similar to early Earth, but increasing solar luminosity and volcanic outgassing gradually thickened the atmosphere until surface temperatures began rising uncontrollably. Once water vapor reached critical concentrations in the upper atmosphere, solar radiation broke it down, hydrogen escaped to space, and oxygen reacted with surface minerals. The process became self-reinforcing as higher temperatures vaporized more water, creating more greenhouse warming that led to even higher temperatures. Eventually, all water disappeared, and carbon dioxide concentrations reached levels that maintained surface temperatures of 900 degrees F. Venus transformed from a potential paradise into an uninhabitable hellscape within a few million years. Earth has experienced less extreme, but still catastrophic climate changes throughout geological history. The Permian-Triassic extinction event 250 million years ago involved rapid global warming that eliminated 96% of marine species and 70% of land animals. Ocean acidification, hydrogen sulfide poisoning, and oxygen depletion created conditions that made most of the planet uninhabitable for thousands of years. More recently, the Paleocene, Eocene thermal maximum 56 million years ago, saw global temperatures rise by 9 degrees F within a few thousand years. This event triggered massive species migrations, ocean circulation changes, and ecosystem collapses that required millions of years for recovery. Even relatively sophisticated organisms struggled to adapt to such rapid environmental changes. Current human industrial activity is driving climate change at rates that exceed most natural variations by factors of 10 to 100. Atmospheric carbon dioxide concentrations have risen faster than at any time in the geological record, except during massive volcanic eruptions or asteroid impacts. The rate of change may be more dangerous than the absolute magnitude of environmental shifts. Advanced civilizations might be particularly vulnerable to climate catastrophe because their technological infrastructure requires stable environmental conditions for optimal operation. Agricultural systems depend on predictable weather patterns. Transportation networks assume consistent seasonal conditions. Energy production systems are designed for specific temperature and precipitation ranges. Even more critically, technological societies often develop population levels and resource consumption patterns that become unsustainable when environmental conditions change rapidly. Modern human civilization supports 7 billion people through industrial agriculture, global transportation systems, and complex supply chains that could collapse if climate systems shift beyond their operational parameters. The speed of potential climate collapse presents the greatest danger. Natural climate variations typically occur over thousands to millions of years, providing time for species migration, evolutionary adaptation, and ecosystem restructuring. But runaway climate change can occur within decades or centuries, faster than biological or social adaptation mechanisms can respond effectively. Computer models of runaway greenhouse scenarios suggest that planetary climate systems contain multiple tipping points where gradual changes suddenly accelerate into uncontrollable feedback loops. Melting permafrost releases methane that increases warming, which melts more permafrost. Declining ice cover reduces solar reflection, increasing warming that melts more ice. Forest fires release carbon, increasing warming that causes more fires. Once triggered, these feedback loops may continue, even if the original driving forces disappear. Venus probably reached its current state through similar runaway processes that continued long after the initial volcanic activity subsided. Earth's climate system might contain similar tipping points that could trigger irreversible changes within human timescales. Ancient civilizations might have triggered their own climate catastrophes through activities that seemed sustainable at the time. Large-scale agriculture, deforestation, fossil fuel combustion, or industrial pollution could have gradually altered atmospheric composition until runaway feedback loops eliminated the civilizations that created them. The geological record preserves evidence of rapid climate changes that coincide with apparent mass extinction events and ecological collapses. Some of these changes might represent natural variations, but others could mark the locations where previous civilizations discovered the ultimate limits of planetary environmental tolerance. Climate catastrophe leaves distinctive signatures in rocks, ice, and sediment that persist for millions of years, creating permanent records of civilizations that push their environments beyond sustainable limits. Every few million years, space rocks large enough to end civilization slam into Earth with the force of billions of nuclear weapons, instantly erasing technological societies and resetting evolution's progress toward intelligence. These cosmic catastrophes operate like civilization reset buttons, explaining why advanced species might repeatedly emerge and disappear throughout Earth's history without leaving detectable traces for subsequent evolution to discover. The asteroid that killed the dinosaurs 66 million years ago released energy equivalent to 10 billion Hiroshima bombs when it impacted what is now Mexico's Yucatan Peninsula. The explosion instantly vaporized thousands of cubic miles of rock, creating a fireball that spread across continents and ejected molten debris into space. Shock waves triggered earthquakes and volcanic eruptions around the globe, while impact debris re-entering the atmosphere heated the entire planet like a giant oven. Within hours, darkness fell across Earth as dust, and smoke blocked sunlight for months or years. Photosynthesis stopped, food webs collapsed, and temperatures plummeted in a nuclear winter that killed most large organisms. The impact eliminated not just dinosaurs, but also marine reptiles, flying pterosaurs, and countless smaller species that had dominated ecosystems for over 160 million years. But the dinosaur extinction represents just one example of cosmic impacts that have repeatedly interrupted Earth's biological development. The late heavy bombardment 4 billion years ago saw asteroids and comets pummeling the inner solar system at rates hundreds of times higher than current impact frequencies. Any early life forms that had begun developing complex behaviors would have been repeatedly sterilized by impacts that vaporized entire oceans. Statistical analysis of crater formation rates suggests that civilization-ending impacts occur roughly every 20 to 50 million years on average. Asteroids larger than 6 miles in diameter carry enough energy to trigger global environmental collapse that would eliminate any technological civilization, regardless of its defensive capabilities. Smaller objects between 1 and 6 miles across could destroy regional civilizations while allowing life to survive in other areas. The timing creates a cruel paradox for intelligence evolution. Complex nervous systems and technological capabilities require millions of years to evolve through natural selection. But asteroids large enough to destroy civilizations arrive frequently enough to interrupt this evolutionary process before intelligence can develop spaceflight capabilities needed for planetary defense. Earth's current asteroid environment represents a relatively calm period compared to earlier epochs. Earlier epochs, when the solar system contained much more debris from planetary formation processes, produced denser and more unstable asteroid belts. These conditions created higher impact rates that would have made sustained technological development nearly impossible. Even advanced civilizations with sophisticated technology might prove helpless against the largest asteroid impacts. Nuclear weapons could potentially deflect smaller objects, but asteroids several miles in diameter carry too much momentum for realistic defensive measures. The energy required to significantly alter their trajectories exceeds current human technological capabilities by enormous factors. The warning time for incoming asteroids varies depending on their approach angles and orbital characteristics. Objects approaching from the direction of the Sun remain undetectable until weeks or months before impact. Even asteroids detected years in advance might be impossible to deflect using current technology if they are large enough to cause global environmental collapse. Ancient impact craters preserve evidence of past civilization reset events, but erosion and geological activity have erased most impact signatures older than a few 100 million years. The oldest confirmed impact craters date to about 2 billion years ago, though statistical analysis suggests thousands of larger impacts occurred during Earth's earlier history. Some researchers propose that intelligence might evolve repeatedly on Earth, only to be eliminated by asteroid impacts before achieving interstellar expansion capabilities. This scenario would explain why the universe appears empty of technological civilizations despite billions of years available for evolution and expansion. The asteroid threat also creates selection pressure, favoring intelligence that develops rapidly once it emerges. Species that evolve technological capabilities quickly would have better chances of developing planetary defense systems before the next major impact occurs. Slow technological development becomes an evolutionary dead end when cosmic impacts operate on geological timescales. But asteroid impacts might also play positive roles in evolution by eliminating dominant species and creating opportunities for new evolutionary experiments. The mammalian radiation that followed the dinosaur extinction demonstrates how catastrophic events can accelerate evolution toward intelligence by removing established ecological competition. The cosmic reset button operates blindly, but its effects on intelligence evolution might be more complex than simple destruction. Understanding impact cycles throughout Earth's history could reveal patterns that explain both the emergence and disappearance of technological civilizations across geological time. Evidence hidden throughout Earth's geological record suggests humanity might not be the first technological species to evolve on our planet, but rather the latest survivors of a recurring pattern where intelligence emerges, flourishes briefly, and then vanishes, leaving barely detectable traces for subsequent civilizations to discover millions of years later. The rapid emergence of human intelligence defies conventional evolutionary timelines. Modern humans developed language, art, agriculture, and technology within the past 100,000 years after millions of years of slow cognitive development. This acceleration suggests evolutionary pressures that exceed what natural selection typically produces, possibly indicating guidance or inspiration from previously existing knowledge sources. Archaeological anomalies hint at more advanced ancient human capabilities than mainstream science acknowledges. Precision stone cutting at sites like Puma Punku requires techniques that supposedly were not invented until modern times. Astronomical alignments in ancient monuments demonstrate mathematical knowledge that exceeds what hunter-gatherer societies should have possessed. These achievements might represent recovered fragments of much older technological traditions. Mythological traditions from cultures around the world describe previous ages when humanity possessed greater knowledge and capabilities before catastrophic events destroyed advanced civilizations. Hindu cosmology describes cycles of creation and destruction spanning millions of years. Greek myths tell of golden ages when humans lived alongside gods who possessed miraculous technologies. Native American traditions describe previous worlds that were destroyed when inhabitants became too technologically advanced. These mythological accounts might preserve cultural memories of real events rather than purely imaginary stories. Oral traditions can transmit information across thousands of years with remarkable accuracy. If previous human civilizations developed advanced technologies before being destroyed by natural catastrophes, survivors might have preserved essential knowledge through mythological frameworks designed to ensure long-term cultural transmission. The distribution of human genetic diversity supports scenarios involving repeated population bottlenecks, where small groups of survivors repopulated Earth after catastrophic events. Multiple genetic studies suggest the human population dropped to fewer than 10,000 individuals several times during the past 100,000 years. These bottlenecks coincide with major volcanic eruptions, asteroid impacts, and climate changes that could have destroyed technological civilizations. Advanced technologies might have been lost and rediscovered multiple times throughout human history. The Library of Alexandria contained accumulated knowledge from ancient civilizations that was permanently lost when the library was destroyed. Similar knowledge repositories could have been built and destroyed repeatedly during previous cycles of technological development. Even more intriguingly, some ancient texts describe technologies that were not reinvented until modern times. Sanskrit epics describe flying vehicles, powerful weapons, and communication devices that sound remarkably similar to aircraft, missiles, and radio technology. While these accounts are typically interpreted as mythological metaphors, they might represent actual technological knowledge preserved in literary form. The rapid development of human technology during the past few centuries might represent recovery of previously existing capabilities rather than completely original innovation. Many breakthrough discoveries involved inventors independently developing similar technologies simultaneously, suggesting underlying knowledge sources that became accessible through some form of cultural or environmental trigger. Underground facilities and artifact caches might contain technological knowledge from previous human civilizations preserved for rediscovery by later survivors. Ancient texts describe hidden repositories of knowledge guarded by secret societies or concealed in remote locations. Some of these repositories might contain actual technological artifacts rather than just written records. The current human population explosion and technological acceleration could be preparing for another cycle of civilization, destruction, and renewal. Historical patterns suggest that rapid technological development often precedes catastrophic collapse when civilizations exceed their environmental carrying capacity or develop technologies that prove ultimately destructive. But if humanity represents the latest in a series of survivor civilizations, we might have advantages that previous iterations lacked. Global communication networks could preserve knowledge more effectively than previous storage methods. Space technology offers possibilities for establishing self-sufficient off-world colonies that could survive planetary catastrophes. Scientific understanding of natural disaster cycles might enable better preparation for predictable threats. The key insight is that survival across geological timescales might require accepting cyclical patterns of rise and fall rather than assuming continuous linear progress. Previous human civilizations might have developed sustainable approaches to technology that avoided the environmental destruction and resource depletion that threatened modern industrial society. Learning from the successes and failures of previous survivor civilizations could determine whether humanity breaks the cycle or becomes another forgotten chapter in Earth's hidden history of recurring intelligence. If we are not Earth's first civilization, then our discovery of this truth represents the ultimate test that determines whether humanity survives to join the ranks of species that successfully navigate the Great Filter, or whether we become another forgotten chapter in the endless cycle of intelligence that rises from the ashes only to burn itself out again. The evidence explored throughout this journey points toward a disturbing conclusion. Nuclear reactors that operated 2 billion years ago, extinction events that happened too fast for natural causes, isotope ratios that suggest industrial activity, and climate catastrophes that mirror our current trajectory all indicate that intelligence has emerged before on Earth, developed technology, and then vanished so completely that only the most subtle traces remain locked in stone and ice. But recognizing this pattern changes everything about our situation. Previous civilizations faced these challenges blind, unaware that others had walked this path before them. We have the unprecedented advantage of potentially learning from their mistakes and successes. The geological record becomes a library of cautionary tales and survival strategies written in the language of rocks and fossils. The great filter that eliminates most technological species might not be a single challenge, but rather a series of increasingly difficult tests that civilizations must pass to achieve long-term survival. Early filters might involve developing technology without destroying the environment. Later filters could involve avoiding nuclear warfare, artificial intelligence disasters, or resource depletion that leads to civilizational collapse. Our current position appears critical. Human civilization shows all the warning signs that preceded previous collapses: rapid environmental change, resource overconsumption, technological development that outpaces wisdom, and social systems struggling to adapt to exponentially accelerating change. We might be approaching the same evolutionary bottleneck that eliminated our predecessors, but we also possess capabilities that previous civilizations might have lacked. Global communication networks allow unprecedented coordination of human activities. Scientific understanding of planetary systems enables us to monitor and potentially control environmental changes. Space technology offers possibilities for establishing self-sufficient colonies beyond Earth's biosphere. Most importantly, we are developing the ability to detect and potentially deflect asteroid impacts that might have repeatedly reset evolution's progress toward intelligence. Planetary defense systems could break the cycle of cosmic catastrophes that have eliminated previous technological species. The search for ancient civilizations becomes more than academic curiosity. It represents crucial research into survival strategies that determined which approaches succeeded and which led to extinction. Understanding how previous intelligence navigated challenges like climate change, resource depletion, and technological risk could provide roadmaps for our own survival. Archaeological investigation of technofossils and geological anomalies should become a top scientific priority. If ancient civilizations left messages or knowledge caches for future intelligence, discovering these repositories could provide technologies or wisdom essential for passing through the Great Filter successfully. But time may be running short. The same geological processes that preserved evidence of ancient civilizations also continue to destroy it. Climate change, tectonic activity, and erosion eliminate traces of the past, while human expansion and development threaten to destroy evidence before it can be properly investigated. Even more urgently, our own approach to the Great Filter demands immediate attention. If previous civilizations failed because they could not solve problems like environmental collapse or resource depletion, we need to learn from their failures while we still have time to choose different approaches. The ultimate test of intelligence might not be developing technology, but rather developing wisdom to use technology sustainably over geological timescales. Civilizations that passed this test might have transcended their planetary origins to become the mysterious absence we observe in the seemingly empty universe. Or they might still be here, waiting to see whether humanity demonstrates the wisdom necessary to join them as conscious guardians of intelligence in a universe that seems determined to eliminate it. The test has begun. Our response will determine whether human consciousness represents a brief flicker in cosmic history or the emergence of intelligence mature enough to light the universe permanently. The choice remains ours, but only for a little while longer.